Good morning. Welcome to this fib webinar. We'll talk about the presentation of the last bulletin on submerged floating tunnel bridges, tube bridges. Sorry. We will do a full day event. First, I will just like to explain you how this will work. And then we will have in the morning an introduction by the fib president, Akio Kasuga, and by Torole Olsen, who was the convener of the group, of the main group. And then chapters 1 and 2 will be introduced by Arianna Minoretti, who led the task group of the bulletin. Then chapter 3, rules and regulations by Bjorn Isaksen, and functional requirements by Cohen van der Vliet. And chapters 5 and 6 that will be said by Annette Field. Then we'll have a lunch break, and then we will continue in the afternoon with the next chapters. Chapter 7, Design Principles by Stein Atle Haugeron. Chapters 8 and 9, Construction and Installation by Gordon Jackson. Chapters 10 and 11, MEP Systems and Operation and Maintenance by Arianna Minoretti. Chapter 12, Risks and Reliability by Bjorn Isaksen, and Chapter 13 and 14, Cost and Study on the SFTB by Torole Olsen. We will have questions and answers after each morning session and afternoon session. I will ask you to try to post the questions in the Q&A that you have or in the chat. And we will have the questions and try to answer them all with all the speakers. This is the opening. I am David Fernandez Ordóñez, the Secretary General of the FIB, and then to continue on with this webinar, I will ask Akio Kasuga to make an introduction on behalf of the FIB as FIB President, and then Torole Olsen as past FIB President. Please, Akio.
Hello, everyone. My name is Akio Kasuga, FIB President, and I'll have a very, very short introduction of FIB. So let me start in a little bit about the history of FIB. And FIB started from 1998, converged to the CB founded in 1953 and FIP founded in 1952. Our slogan of the FIB is a bridge between research and practice. Now we have 41 statutory members countries like this all over the world, and we have members 104 countries and territories, including the individual members. And this is our mission and objectives that we started from the stimulation of research and some findings, and also transfer to design and the construction practice. And after that, and this is very important, dissemination by publications and the conference and so on. And finally, we product the recommendation and the cause. And again, with dissemination of the informations to all of the members. This is our main activity of the FIB. And this is a structure. We have a technical council and the general assembly, and we have presidium, and we have many commissions from Commission 1 to Commission 10. And today's the webinar, the output from Commission 1, concrete structures. And this is the members of the FIB from 2021 to 2022. Torole was the past president from 2019 to 2020. We have a variety of countries from all over the world. And our main output is bulletins from each commissions. We have some categories from technical reports, state-of-the-art reports, textbook, manual guides, and recommendation, and model code. And also we have the journal of the structural concrete. Currently, our impact factor was 2.174. It's a relatively large number in the civil engineering magazine. And we have 6 issues from 2016. We have many backlogs, and also every time the number of papers increasing. So our biggest event of the output is the launching of the model code to the world. So now we are just revising the last model code 2010, and we will launch to the model code as a model code 2020, and including leading edge technologies and many contents of the concrete structures. Okay, so let me tell you some upcoming events. That we have the symposium next month in Lisbon. Unfortunately, we have totally online symposium, but we have many papers will be presented here. And also the PhD symposium in Paris, France in July. This is also online. And ICCS 21 symposium in Prague in September, and the conceptual design symposium in Switzerland in September also. And also the 2022 with the big event of the FIB Congress in Norway, and also the same year the symposium in Italy. Please come and join us. Each event is very interesting for you. And we have many output, bulletins and the symposium, and also we had output using social media. We have FIB News, e-newsletter, and these social media can be used to get information from FIB. And also at the same time, we have a webinar in the YouTube channel like today's event. We have many variety of speakers. Each speaker has very interesting topics. Please come here and to join the webinar. And one of our most attractive activities for the young members group. And now the commission chair is Motohiro Ono from Tokyo University, and each country has a very active young member group. And this member group can be joined as a personal or not if your country is not a national member group. So please join us. Please exchange your information all over the world. And also we have collaborated with the same organization, ACI, RILEM, ALCOMPAT, and ACF, and we had a very close communication to make a joint activities and joint publications. And today, the submerged floating tube bridge is the output of the working party 1.2.2, belonging in the task group 1.2, the combined Torole. This is a task group for the concrete structures in marine environment. It has been working a very long time, and today's output, Bulletin 96, is very interesting, as you know. Okay, so marine structures has very long history, and I think it is one of the innovative technologies in FIB's activities. About 40 years ago, they have the technology of the oil leak for especially Northern Sea. And now that this technology extended to the wind turbine on the sea, and also today's topic of the tube tunnel under the sea. And the Tororo said in 2070, the temperature of Earth is rising, and also the water level is rising. They are thinking about floating residential houses like this. And at the same time, if the temperature of Earth is rising, and also the human might be live under the sea like this. So this the structure for the concrete in the marine is continuously to lead to all of the possibilities in the future. So please enjoy the webinar today, and thank you very much for your attention.
Hello, everyone. We continue with marine structures. Before we go on to the real content of today's webinar, I will say a little bit general about marine structures. Yes, most of us like the sea, and the sea is also very useful for many purposes. The ship to the right here carried Norwegians across the North Atlantic some 1200 years ago. So ships have been used for all times. Marine floating concrete structures come in all sizes. The picture to the left is Lambot's boat, concrete boat from 1848. That's a little one. And then you have bigger ones to the right. The smallest structure there is the City Hall of Oslo that you can see by yourself if you come to the Congress next year in Oslo. There are some distinct differences between designing and constructing ordinary land-based concrete structures compared to marine concrete structures. And I will try to highlight that a little bit. Akio already showed this. One of the commissions is Commission 1, Concrete Structures. And within Commission 1, we have the task group 1.2, Concrete Structures in Marine Environments. And the red one here is what we're talking about today. A couple of years back in 2019, we produced a Bulletin 91 named Floating Concrete Structures. And the Submerged Floating Tube Bridge is working party 1.2.2. And at the moment, we have no more working parties we are discussing, and if any of you have any suggestions, we welcome them. The Bulletin 91 floating concrete structures look like this. We have previously produced a couple of bulletins, recycling of offshore concrete structures some years back, and then concrete structures for oil and gas fields in hostile marine environments. Now, why are FIB interested in marine concrete structures? And in Bulletin 91, we listed 12 potential usages. There may be more. If you are creative, you may find many more. Some examples here, you have military actions. We don't write much about that in Bulletin 91, but this picture is of the Mulberry Harbor that the British built towards the end of World War II to aid invasion of Normandy. This is a concrete platform for oil production. This is a floating bridge in the state of Washington. And this to the right is a harbor extension in Monaco. And as you will know, Monaco is not having very much space. So space is one of the factors that concrete marine structures can help out with. And you have energy. And actually, if you look at these 12, you will see that many of them are related to environmental issues. I've tried to illustrate very simply some of these usages. Akio already showed you this one. I have added here, you cannot read my handwriting, but it says tsunami. This is actually a real situation maybe in the future. Another usage of marine concrete structures is for attractiveness. If you live here, you might wish that you lived here. You have a foundation issue. You have the use of land. Do we need to have buildings everywhere in our cities? Construction issues and challenges, environment and pollution is an important factor. But there are some challenges. You cannot build a high-rise on the edge of a barge because it will tip and maybe capsize. And some of you have experienced this if you have been in a small boat half filled with water. And you have, for real structures, you have some challenges, waves and ice. But you have also a very large beauty, and that is the beauty of buoyancy. This structure here weighed 1.5 million tons when it was transported from here, several hundred kilometers, and installed. And lifting 1.5 million tons is not possible anywhere else than in the sea. This structure carries 22,000 tons, 150 meters above sea level. So with the buoyancy, it is a real beauty, but you need to make sure that it relates to the gravity. Both gravity and buoyancy is an act of Mother Earth. So both the size of the weight and buoyancy should match, but also the location. If they don't match, you may have serious problems. You may sink or you may capsize. And how do we create this buoyancy? And this is a very simple sketch, a cylindrical bucket. And it is the bucket that provides the buoyancy. And if you make your own calculation on a very simple model like this, you will illustrate the effects of concrete unit weight, concrete strength, and wall thickness. And this is, I think you can realize that if the concrete is very heavy and the strength is very low and the loads are high, you may have difficulties. So this is why so much useful research has been done on lightweight concrete and high-strength concrete. Another maybe a little bit surprising example, if you have a square bucket where the water pressure is carried by bending, you may be tempted to increase the wall thickness to reduce the amount of reinforcement. But by doing that, you also increase the load. So you can show that increasing the wall thickness gives you a more expensive structure than keeping it slender. Yeah, this little picture down to the right is the prototype of the Condip. Condip is a concrete platform for oil and gas production. And these are the 15 Condips that have been built. There are others in the world. You have 2 that sits in Canada. You have 2 in Australia. You have 3 in Russia. And you have a gas, LNG gas plant in Italy, in the Adriatic. So these all together 29 offshore structures for the oil and gas. All together in the world, there are 50. And they behave well. We know because we have tested them. Some of them are priced. This is a Norwegian stamp. And most likely it was not the structure, but the amount of money that comes in from the sale of gas that made them make the stamp. This is another one priced. This is an Angolan bill. So why they put our platform on that, I'm not quite sure, but they do. Another aspect of floating concrete structures is that you have a lot of loads. You have ballasting and you have waves and wind from all directions. And to take care of these, we need some routines, obviously. And we need also to keep our minds clear what is what. It's a logistic part of this to keep track of all the numbers and all the load combinations. And we use, today we use obviously finite element analysis for the structural analysis. We have now included also nonlinear iteration, even for large global analysis with several million degrees of freedom. And this is necessary to design these structures. And a simple explanation for why nonlinear analysis is important is that the old fashion of just modeling stiffness by the thickness of the concrete structure is very incorrect, particularly if you have very little tension, tensile reinforcement. You see that you get both unconservative and conservative results using the old method. If you are working with structures that do not resemble laboratory type structures, you need real models also for shear. And for this purpose, you can now include the modified compression field theory that gives you much better results if you, particularly if you work with unusual structures. Now, this is a picture of salmon. They are normally bred in a net structure. The net structure allows lice and other parasites into the salmon and harm them. It's not very nice to be an animal and be harmed like this. So we have worked a lot with making concrete buckets to prohibit this. But we have a challenge, and that is a concrete wall is typically more expensive than a net. But nevertheless, we have designed and built small buckets. We are using styrofoam to achieve buoyancy. Very thin walls, 100 millimeters. And this is another structure, but we have utilized our computer tools to document that we can get away with single layer of reinforcement. That saves weight. The pink here is again styrofoam. And you should always remember that the structure has a purpose, and you need to include that in your design. This is a larger fish farming area, and you can see that the equipment to be able to produce fish is rather extensive, actually. Salmon use a lot of fresh water. Akio mentioned dwellings. This is a concept for apartment buildings, and you may see that we have made the structure symmetry to make sure that the structure doesn't tilt too much. And then a few words on conceptual design. You have good designs and you have not so good designs. Sir William Lyons designed this car in 2 weeks in 1948. You need a lot of courage because if you start in the very, very safe end, you may never end up with a structure that floats. You can use untraditional tools in conceptual design. We use a lot of shell structures because shell structures are efficient in carrying distributed loads, so they are light. We do testing also with the soil. This is dirt piling experiments. The concrete walls are pressed into the soft clay to find a stronger foundation. This is the first page of the conceptual design. You have a lot of freedom. This is just to show an example where the original design had 42-inch gas pipes running outside a platform, a water-filled platform. You cannot have gas-filled pipes within water. And then they are turned into the structure below the sea level in a spaghetti-like fashion. You may choose to crook the concrete wall and let the real function of the platform be straight instead. This is from our laboratory. This is a wave energy device that is now actually built and placed outside Portugal. This is a 12,000-ton deck, and it doesn't look like it, but this is actually fun to do this kind of work. And that was what I had to say for the introduction on general actions on concrete marine structures. Thank you very much.